All right, welcome to our second set of notes from section 8.2. We're talking about permutations and probability. Now, permutations is very much related to last week's work on the multiplication counting principle. And so before we dive into permutations, I just want to remind us of what the multiplication counting principle said, because it's really just one extra step beyond that to talk about permutations. Okay, so remember, the multiplication counting principle is this idea that if we're trying to count the number of possible outcomes, you could write out the sample space, right? So if I have a sandwich, I'm going to pick bread, one of these meats, one of these condiments, let's say. So I could do the sample space. I could do wheat, turkey, mayonnaise, wheat, turkey, mustard, wheat, turkey, ketchup, wheat, salami, mayonnaise, wheat, etc. I could do all these different things here. I can count them all out that way. Or multiplication counting principle says if I've got 2 possibilities for bread, 3 possibilities for meat, and 3 for condiments, I can just multiply that together and I can get 18 possible, right? Much easier than just counting out all these. Okay, so you count out 2 possible here, 3 possible here, 3 possible here, multiply that, that is the total number. Okay, permutations is very much related, so let's just do a couple more and kind of transition naturally to talk about permutations. Okay, so again, last time we talked about license plates. So if you have a license plate beginning with 1 letter and 3 digits and 3 letters, let's say there's no restrictions, you can start with any letter, any different combinations are fine, you can repeat them. What that's saying is that, again, you could just go like this and say how many possible license plates are possible. It's 26 times 10 times 10 times 10 times 26 times 26 times 26. In other words, 26 to the 4th power times 10 to the 3rd power, which is about 456 million different combinations. Again, why is that? Because I've got 26 possibilities here, I've got 10 possibilities here, I've got 10 possibilities here, 10 here, 26, 26, 26, because you can repeat. Okay? Now, what if I didn't allow repetitions, right? If I didn't allow repetitions, the key is it's going to go like this: 26 times 10 times 9 times 8 times 25 times 24 times 23. So it's still a lot, but it's 258 million instead of 456 million. Why the difference? Again, because if you cannot repeat, picture it like this. You have every possible letter available to this first one, but once you've picked it, let's say you use F for the first one or whatever, then you have only 25 numbers left for the second letter. And then once you pick another letter, let's say A, then you have only 24, and then you have only 23 for the third one. Likewise for the numbers, you have 10 possibilities for the first digit, but then only 9 possibilities for the second and 8 for the third. So that's why you're kind of doing this countdown thing when you don't have, you cannot repeat. Again, this idea is going to be key for permutations as well. Just a couple more examples. So if I have 10 different flags, I want to arrange them in a linear pattern, okay? So again, you cannot repeat flags, right? You're going to arrange them. So like if you pick one flag for here, you cannot use it again. So just like we talked about before, it's going to look like this, right? You pick, let's say you pick the flag of India, I believe, for this one. And then you pick the flag of Great Britain for this one. Then you pick the flag of France for this one, right? You have 10 choices for the first possible flag. And then you have 9 choices because you use that one for the second one. And you have 8, and then 7, and then 6, so on and so forth. So it looks like this, right? 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which instead of writing it like this, because this is a very common thing, we write this as factorial, 10 exclamation point, 10 factorial, or about 3.6 million. Again, for your calculations, if you want to go to Desmos.com, you just type in 10 exclamation point, and it gives you that same number, about 3.6 million ways. All right, so now let's talk about how does permutations fit into this. It's very similar. Here's the key. If let's say you don't want to use all 10 flags, you have 10 possible flags, but you're only going to use 3, you're only going to hang up 3 flags on your window or something like that. You have 10 possible, but you're only going to use 3. This is really what a permutation can count for you, okay? So just think, how many possible do I have for the first flag? How many possible do I have for the second? How many for the third? Right, so just like before, I've got 10 possible here. I pick that one, so I have 9 possible, and then 8 possible. And I don't go all the way down 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 because I'm only using 3 flags. So it would look like this. 10 times 9 times 8, stop, and that's 720. 720. So you cannot use, you cannot say 10 factorial. I'll show you in a second the formula, but for now you could even just do it like this for most of the problems. In fact, actually for all the problems. involving permutations, you can just use the multiplication counting principle. What if you have 10 flags, but you only want to pick 2? Again, same thing. Think about how many possibility do you have for the first flag, how many possible for the second? Same thing, right? 10 possible for the first flag, 9 possible for the second, so 90 total ways. One last quick example before we get to formula. So let's say we've got 27 students in the class. Let's say I want to rearrange the seating chart. How many different seating charts are available? Okay, so one key with permutations that we won't really highlight until we talk about combinations is that order matters. So if student Joe sits here and student Katie sits here, that's different than if Katie sits here and Joe sits here, right? Joe, Katie is different than Katie, Joe. We see that order matters. Different arrangements produce different outcomes. Again, that'll be key when we talk about combinations later, but for now, just think of it as permutations means the order matters, okay? So I have 27 different students. I want to use all 27 seats. Again, it'd be this gigantic possibilities. You have 27 possibilities for the first seat. Then you have 26 students available for the second, and then 25, and then 24, and then 23, 22, 21, 20, 19, 18, 17, 16, 15, 14, all the way down to 1. You can also write that as 27 factorial, which is, again, a giant number. So 1.08 times 10 to the 28th, which is, again, 10 with 27 zeros after it. So it's just gigantic. All right, now permutations, though, answers the questions for us. What if I don't want to use all 27? What if, for example, I just want to pick 2 students? Let's say I pick the students sitting here as the president, and this one as the secretary for the class. That doesn't really make sense. We don't do that, but whatever. So again, order matters because Joe being president and Katie being secretary is different than if Katie was president and Joe was secretary. So you can just use the multiplication counting principle. How many choices do you have for president? How many do you have for secretary? Like we talked about, you have 27, if there's 27 students, 27 possible for president, 26 possible for secretary, because that first person already sat here, so 702 possible. All right, so now this will lead us into the formula. Again, as a quick reminder, factorial just means this exclamation point. It's the number times 1 less, times 2 less, times 3 less, all the way down to 1. So 4 factorial is 4 times 3 times 2 times 1, or 24. 5 factorial is 5 times 4 times 3 times 2 times 1, or 120. So you can just test those out. And again, the numbers get really big really fast, right? 4 factorial is pretty manageable. 10 factorial is huge. If you try to do 100 factorial, I don't even know. Yeah, just astronomical. So 9 plus 157 zeros after it. So insanely huge. Permutation. So what we've been talking about, what we've been leading up to. Permutations is an arrangement of objects in which order is important. And again, we'll highlight that when we talk about combinations, but basically, if I have student A, B, and C, it's that A, B, C is different than A, C, B, which is different than B, C, A, which is different than B, A, C, C, A, B, C, B, A. All these count as different outcomes. So permutation, right? You're counting the number of possibilities. You're picking. So here, this formula looks kind of confusing, but we'll see how it really is just what we've been doing with the multiplication counting principle. Again, in fact, with permutations, you can just use the multiplication counting principle if you want. So what you do is, the formula is this, NPR. The N is the total number you're selecting from. So for the flag problem, it's like 10. So from 10, I have 10 flags. I'm picking let's say 3 flags to arrange. So 10P3. What it is to put the N factorial on top over N minus R factorial. So N factorial over N minus R factorial. And it looks confusing. We'll see how it really is just what we've been talking about before. So let's say I'm picking, I have a small class of 11 students. I'm picking president, vice president, and secretary. Let's say it's random, it's not voting. So first we ask, again, as a way to distinguish between combinations, which we'll learn later, does order matter? So in other words, if Abel is president, A, and vice president is Bella, and secretary is Carlos, is that different? Should that count differently than president Carlos, vice president Abel, secretary Bella? If yes, use permutations. And in this case, yes, right? A, B, C is different than C, A, B. I should count those separately. Okay? So again, you can use the multiplication counting principle. How many different possibilities are there for president? Well, there's 11 students, so you can say 11. Then I pick that student there, etc. So I have 11 times 10 times 9. So I punch those in, that's 990. The permutations formula, again, goes something like this. We say 11, so we say I'm picking from 11, this is the total number, P, I'm picking 3, right? I'm picking president, vice president, secretary. I'm picking 3. And how that formula goes, again, you put 11 factorial on top over 11 minus 3 factorial. 11 minus 3 is 8. So it looks like this. 11 factorial on the top in the numerator, 8 factorial in the denominator on the bottom. And still that looks confusing. How is that related to this? But if you think about it, 11 factorial is 11 times 10 times 9 times 8 times 7, 6, 5, 4, 3, 2, 1. I'm just going to write that as 8 factorial because I ran out of space here. Over 8 times 7 times 6, 5, 3, 2, 1. But if you notice, all these 8 factorials are going to cancel each other out, right? 8, 7, 6, 5, 4, 3, 2, 1 on the top. 8, 7, 6, 5, 4, 3, 2, 1 on the bottom. They cross off. That just becomes one giant 1. And you're left with 11 times 10 times 9, which is exactly what we had over here. So it gives you the exact same answer, 990. So the formula will give you the same thing as if you use the multiplication counting principle. Let's do a few more examples. Let's say you have an 8-woman race in Olympics and you're picking to win gold or silver. How many choices do I have for gold? How many choices do I have for silver? Well, again, I've got 8 possible women racers that can finish first, and then that person's picked, so they have 7 left. So there's actually 56 different ways total. Again, we're counting the number of ways that this can happen, right? If they're named person A, B, C, D, E, F, however, A, B, C, D, E, F, G, H. You could have person A followed by person B, or person A and then C, and then person A and then D, or B and then A, B and then C, B and then D. There's 56 different combinations to finish gold, silver. Okay? Permutations formula, again, looks like this. What you do is you put the total number you're picking from on the left-hand side, 8, that's an 8-woman race. P, how many are you selecting for arrangement? 2, right? Gold and silver only. And again, the formula goes 8 factorial on the top over 8 minus 2 factorial on the bottom of the denominator. So over 6 factorial. And again, what that's saying, 8 factorial is really just saying 8, 7, 6, 5, 4, 3, 2, 1. 6 factorial is just 6, 5, 4, 3, 2, 1. But these just cross off. And so you're really just left with 8 times 7, which is again the same thing as doing the multiplication counting principle. So you could do either one here and you get 56 ways. Okay, so let's do a couple more problems and to finish up, and let's do probability. Now this is tricky, so if you're kind of confused by this, just kind of stick with it, watch it, and if you have questions, watch over it again or email us. But let's take a look here. So for probabilities, you kind of have to do 2 problems in one. Probabilities, again, what you're doing is you're picking on the bottom, you're figuring out the total number of possible outcomes. And then in the top, in the numerator, you're counting the total number of ways to get success, what you are looking for. So let's say I've got a bag with letters A, B, C, D, E, F, G. 1, 2, 3, 4, 5, 6, 7 total letters in it. You're going to pick 3 of them randomly, and you're going to win $1,000 if you pick A, B, and C in any order. So like you pick an A, followed by a C, followed by B, or a C, and then A, and then B, or a C, B, A, etc. You get $1,000. And $10,000 if you pick A, then B, and then C in exactly that order. What is your probability of winning $1,000? In other words, what's your chance of picking an A, B, and C in any order? Okay? So first off, let's think about the denominator. How many different ways are there to pick A, B, C, D, E, F, G? Pick a subset of 3 total. Okay, I pick a subset of 3 total. Well, that is going to be, again, you can use the multiplication counting principle or the formula. I'm just going to pick the formula. So we get and think, how many am I picking from? How many am I picking? So it goes like this. Again, I've got 7 possible letters. So from 7, the bigger number goes over here. From 7, I'm permuting 3, right? I'm grabbing 3 letters randomly. So I'm grabbing 3 from 7. Okay, and again, the formula goes 7 factorial on the top, 7 minus 3, or 4 factorial on the bottom. And so what it is, it's 7 times 6 times 5 times 4 times 3, 2, 1, and then over 4, 3, 2, 1. And again, these just cross off. So I'm left with 7 times 6 times 5, or 210 possibilities. Again, you could just use the multiplication counting principle instead and say, I've got 7 possibilities for the first letter, 6 possibilities for the second letter, 5 for the third letter. That's fine as well. So that's, again, you're counting the total number of ways to pick 3 letters from 7. And then let's think on the top, in the numerator, how many possible ways are there for success? Now, how many different ways can you get an A, B, or C in any order? Now, this is so small, you could actually just count the sample space. But we can also use the multiplication counting principle or the permutations formula. So think, how many ways could I arrange A, B, and C if I count them differently, like A, B, C, A, C, B? Well, it's just this. Again, you could just do the sample space. A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, C, B, A. There's 6 possible ways. But you could also do the multiplication counting principle. You could say I've got 3 possibilities for the first pick, right? Because A, B, or C, any of those 3 would work. 2 possibilities for the second and 1 for the third, or 6 possible ways. So in other words, I've got 6 possible ways to have success over 210 total possibilities. And to illustrate this, I can actually show you the sample space, right? So again, out of 210 total possibilities, 6 of them end up with some A, B, C in some order. And so here it is. There's a generator that I can use online, so don't worry, I didn't type this up myself. But again, you're picking 3 letters from 7. You could have A, B, C, A, B, D, A, B, E, A, B, F, blah, 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 D, A, G, D, B, A, D, B, C. There's 210 possibilities. Of those 210, 6 of them end up with A, B, C in some order. A, B, C, A, C, B, C, A, B, C, B, A, B, A, C, B, C, A. 6 out of 210. So our probability of winning is 6 out of 210, or about 2.8%. All right, now what about if I want to get exactly A, B, C in that order? Exactly A, B, C. Now this one's actually a little bit easier. If you think about it, we've got our sample space here. Again, it's the same thing. There's still 210 possible ways. I could use the formula. I could use the multiplication counting principle. Before we use the formula here, I could just say, use the multiplication counting principle. I've got 7 possible letters for the first digit, for first letter 6, and then 5, so 210 possibilities. Out of those 210, how many ways are there to get A, B, C in exactly that order? Again, there's 6 possible ways to get an A, B, or C, but only one of them is in exactly that order, so I say 1 out of 210. So it's much harder because you have to get A, B, C in that exact order. And again, these are tricky. Don't worry, it's tricky because it's like 2 problems in one. We'll just keep doing examples. All right, last question. Let's say in the Kentucky Derby, I've got these horses, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 possible horses. Let's say all horses are equally likely to win, so it's just kind of random. What's the probability the race will finish with Promises Fulfilled, this one, Magnum Moon, Enticed, and then Flameway? 1, 2, 3, 4. Those are the top 4 in any order. So again, what you're going to do is like 2 problems in one. You're going to calculate how many different possible ways are there for these 10 horses to finish 1, 2, 3, 4. Again, order matters, so you can use the multiplication counting principle. You can use permutations. And then of those, how many different ways are there for those 4 horses to finish in that top 4 in any order? Again, you can use the multiplication counting principle. You can use the permutations formula. It's a little bit more, it might be kind of annoying to write it out, so I probably wouldn't write out the sample space, but I guess you could. So pause the video and try this last question. It's quite tricky, so try it. All right, so it could look something like this. Total possible outcomes. Again, where do we get this number? It's because I've got 10 horses. From those 10, I'm picking 4 of them. I'm picking 4 of them. So 10P4. 10P4. Again, you could use the multiplication counting principle as well. 10P4. I'm picking from these 10, 4. Okay, so again, 10 factorial goes on the top in the numerator. 10 minus 4, 6 factorial goes in the denominator. And you just, again, you can write out 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, but you could just stop here because the 6 factorial over 6 factorial just cancels out, crosses off. You get 10, 9, 8, 7. By the way, on Desmos, if you want to do the permutations, I believe you can just type NPR parenthesis 10, 4. Yeah, there we go. So you don't have to do the formula. You can just type in N. I believe you need a capital P. Yeah, capital P, R, parenthesis, and then you just say whatever you're trying to do, 4, 4, or whatever. Okay, so again, the bigger number is how many you're picking from. I'm picking from 10 horses. I'm selecting 4 of them to arrange because it's the top 4. So if you want to go to Desmos and just type in NPR parenthesis, it'll give you the answer. Okay, so or I can just do it like this: 10 times 9 times 8 times 7 is 5,040 ways. So again, there's 5,040 ways for these 10 horses to finish in the top 4. Note, again, the multiplication counting principle is also totally fine here. You can say, I've got 10 possibilities for the first horse to finish. Then I've got 9 possibilities for the second place finish. Then I've got 8 possibilities for third place finish. And then 7 possibilities for fourth. Okay, now how many ways are for these four? Promises, magnum, enticed, flameway to finish in the top four. Okay, you could do the multiplication counting principle, you could write out the sample space, or the formula. And so actually probably easiest to use the multiplication counting principle. You've got, okay, I've got these four, so I want, I have four possibilities for the first horse, for first place, and then three possibilities for the second, and then two, and then one, 4 times 3 times 2 times 1. That's 24 ways. Or you can think of it as I'm picking 4 out of 4, so 4p4. That looks kind of weird, but it's a valid way to do it. So I'm picking 4 horses from these 4 to arrange. So it's 4 factorial over 4 minus 4 factorial. Now 0 factorial is defined as 1. So we just write 4 factorial over 1, which is 4 times 3 times 2 times 1, or 24. Again, you can also just type NPR4, 4, and it'll give you the same answers. So again, it's saying there's 24 ways for these guys, promises, magnum, enticed, flameway, because it could be magnum, promises, flameway, enticed, enticed, flameway, magnum, promises. There's 24 possible arrangements of those guys to finish in the top 4 out of 5,040 total. And so my answer is 24 out of 540. You can also write 4p4 over 10p4. Punch that in Desmos or your calculator. It's about 0.4%, 0.47%, so quite low.